Good morning, everyone. Can you hear me well? Yeah, in the back? Okay. Good morning. As David said, I'm Marta Reina-Campos. I'm a CITA Canada Fellow at CITA, and I also spent 2 years among Master. And I'm what some people in the room have called themselves a baryons person. I don't do that matter. For me, that matter is just CDM. But I want to kind of give you an overview of how can we model galaxies over cosmic time. So I'll just use my laptop. Okay. So how can we build galaxies over time? Like, what are the critical ingredients that we need to put in the computer to do this type of numerical simulations? If we look at the cosmic microwave background, this is imprinted with tiny temperature fluctuations that indicate that back at the epoch of ionization, the distribution of density was not uniform in the universe, but actually had tiny fluctuations. So there are regions in the universe where the density was higher, and because of gravity, those regions were going to collapse into what we know of the large-scale structure of the cosmic web. So the first thing that we need to include in our numerical simulations is gravity. We need to include the gravitational collapse of dark matter, and now I'm going to let you argue which is the right one, that collapses into large-scale structures and regulates the movements of the stars within galaxies. But we also have gas in the universe, or this baryonic matter. And so we also need to account for the equations of hydrodynamics that are going to describe how the gas move. And in particular, they're going to require the conservation of mass, momentum, and energy. In this picture of the cosmic web, where there's this large-scale structure that's collapsing and it has the gas, it can lose energy, and therefore it can lose angular momentum, and it can collapse into what we know as galaxies. Within these clamps of within these structures, further cooling of the gas is possible via particle interactions and emission of radiation. So the gas is becoming cooler and denser over time. And as that happens, there is a moment in which the gas can fragment into certain sizes, and those fragments can start igniting nucleosynthetic processes within them. This is what we call a star. If there's fragmentation, but there's not nucleosynthesis, that's what we call a brown dwarf. But once the star formation happens, or starts happening within a galaxy, we get a population of stars within our galaxy. And what's really interesting is that the properties of these stars are not uniform throughout the galaxy. So if we look at the masses of the stars, we know that there's a certain distribution that we call the stellar initial mass function. It's debated exactly what is the exact slope of that distribution, and whether the slope is universal, whether it depends on the environment, what is the most massive star that you can form. But in general, what we see is that not all stars have the same mass, and that when stars form, they do not form in isolation. The vast majority of stars form in clustered regions. And if those regions have sufficient mass and they're dense enough, they're going to stay gravitationally bound. And this is what we know as star clusters. So star clusters are these gravitationally bound systems of stars that they form all clusters together and kind of remain bound throughout the lifetime. And we'll see later what that is important for the evolution of the galaxy. What's really important to consider, and it's not being considered in galaxy simulations at the moment at all, is the fact that observationally, we know that all massive stars are in multiple systems. So they're in binaries, tertiary systems, or higher order multiples. And being in a binary can alter the evolution of stars, because if you have a very massive star together with a low mass companion, the massive star can, there's a disbalance of mass, but they can share masses between them. And if you change the mass of the star, you're changing their evolution. So you're changing, for example, when the time of the first supernovae happens. The vast majority of numerical simulations of galaxy formation assume that the first supernovae happened within 3 mega years, because that's true for a massive star in isolation. But if that massive star is in a binary, that first supernovae can be delayed up to 10 or even farther down its evolution. And it can also alter not just when the first supernovae happen, it can alter the amount of radiation that you get of the star, it can alter the chemical yields that you get into the star, and so the amount of metals that you have in your galaxy. So over their lifetime, their stars are doing the different nucleosynthetic processes within its core. Their star burning hydrogen, and then they go into helium and higher order elements depending on their mass. And as they do that, they're shedding out the outer layers of the star. So they're shedding out mass, they're leaving out energy, they're impacting momentum and radiation into the medium. So all of these processes is what we typically refer to as a stellar feedback. And you may have heard of different types of feedback, things like protostellar jets, the supernovae that I was talking about earlier, which is the final explosion of massive stars. But we also have to account for the impact of luminosity, stellar winds, and all sorts of different types of mechanisms. So when the stars burn out all of the nucleosynthetic fuel that they have in their core, they cannot support the gravity of the stars, so they collapse. They first collapse, and then there's a final explosion as to a supernovae. That's true for the most massive stars. And then the remnant that they leave behind is a black hole or a neutron star. When these remnants are in binaries, then they might merge, and this is what we see from a gravitational wave, or like as gravitational wave emitters. But in galaxies beyond the stellar population, we also have dust. So dust are silicates most of the time, and they can absorb the blue light coming from the stellar light, and it can be re-emitted into the infrared. And these at first might not seem like a big effect, but if you're trying to do radiative transfer within your numerical simulation, you have to take into account that some of the light that is being emitted in the UV is actually being displaced into the infrared band. So the way that it affects the gas, how it's cooling and how it's heating, needs to take into account the effect of the effect of dust. In addition, we know that there are magnetic fields in the universe. They do all sort of funky things to your gas, but one of the things they do is that they can support the interstellar medium, so the gas within the galaxy, and prevent its collapse. So if you really want to do galaxy simulations well, you should include magnetic fields, although the vast majority of simulations don't include them because they're complicated. And in massive galaxies, we see that there are supermassive black holes in the center of the galaxies. So one should include the fact that there are these black holes, and the fact that these black holes are accreting gas from their surroundings, and they're outputting some feedback in the form of powerful jets. And this is what is often referred to as active galactic nuclei feedback. And in addition to all of these different astrophysical processes, we have things like cosmic rays. This is something that's starting to be quite common in the literature. People are adding more and more models of cosmic rays into their simulations. You might also want to take into account that the plasma in the galaxy is not just a single fluid, but it's actually several fluids. If you're doing magnetic fields, you might have non-ideal MHD. You might account for neutrinos, and as the goal of our workshop, you might account for the fact that actually dark matter is not CDM, or we don't know what it is. But there are other possibilities for dark matter models that you might want to take into account for your numerical simulation. So I really like, trying to model galaxies is a really difficult problem. And it's really challenging because it's a multi-scale and multi-physics problem. I really like this figure from a recent review by Rob Kren and Floor van den Voort from just last year, where it's showcasing the huge range of scales that we have to take into account when we're trying to do galaxy formation. So when in the field of galaxy formation, we might take into consideration things like the largest scale structure of the universe, the scale of galaxy clusters, or the circumgalactic medium, so the gas surrounding galaxies, the size of galaxies, the interstellar medium, so the gas within galaxies, stellar clusters, or the stellar populations within the galaxy. We might take into account physical processes that happen at the scale of binary stars, or around black holes, or in the size, like at the size of stars. So the way I like to think of numerical simulations is that they're numerical experiments. In astrophysics, we cannot go to the lab and do an experiment, but we can go to the computer, put in the equations that we think are relevant, and see what happens. So my view of numerical simulations is that you first need to choose what you want to study. And so you kind of go into this spiral and you say, okay, in my case, I'm interested in how galaxies and their stellar populations form. So I need to concentrate on all the physics that go between the scales of galaxies all the way up to kind of like the stellar populations. And I need to make sure that the physics that act on these scales, or kind of that can influence these different systems, are the best representation that I can have. But for things that are smaller than my stellar populations, I cannot really resolve them. They're not relevant for my problem. So I'm just gonna mimic them using subgrid physics or subgrid methods. So these are gonna be approximate methods that describe all of the things that I cannot actually resolve in my simulation. So I will not account, for example, for stellar, like for the fact that if stars are in binaries, that might affect stellar evolution. I will either ignore that, which is what the vast majority of people do, or I'll just come up with an analytic prescription that it's not going to be realistic, but it kind of gives you a zero order idea of how it works. And so you kind of account for everything that's below that as subgrid physics, and then everything that's above, you say, these are my initial conditions. So for example, if I change dark matter in my numerical simulations, I'll just kind of change what sort of power spectrum I use to generate the initial conditions of my galaxy simulations. And that's all I'll do. Or add other terms in the equations if that's relevant. So this is a very messy figure, also via a recent review on galaxy formation, kind of describing what do we need to include in numerical simulations. This one is Mark Vogelsberger, but kind of we can break it down into the different subsections. And so this figure is telling us, okay, if you want to do a simulation of that describes the formation and evolution of galaxies, what are the different things that you need to take into account? There's like a beep. Is it me or is it? Okay. So the first thing we have to take into account is what's the cosmological framework. So what are the actual equations we want to use for gravity? What do we want to assume for dark matter? So this is the goal of the workshop, kind of describing all of these different models, and whether you want to include inflations and what kind of initial conditions you're going to be using. Then you need to say, okay, whoops, for the numerical experiment that I'm setting up, which of these different astrophysical processes are relevant to my problem, and how am I going to include them? So in my case, because I want to do galaxies with stellar populations, I know that I need to have a really good description of how the gas cools, because I need to be able to model the multi-phase structure of the interstellar medium. So the fact that the gas within galaxies has a really cold and dense component and a warm and hot diffuse component. I need to have a good description of how star formation and stellar feedback happens, but I don't really care about supermassive black holes because the type of galaxies I do not really have a lot of AGN feedback, so I can forget about them. I can forget about magnetic fields. I should include radiative transfer because ionizing radiation is important, but I can't forget about cosmic rays. So that already kind of gives you an idea of what sort of ticks you need to include in your simulation. The next thing is to say, okay, what am I going to be running? Do I need to be running an individual galaxy to study the problem that I have in hand? Or do I need a large sample of galaxies to extract the statistics to understand what's going on? Here, there's a trade-off between what you want to study, what physics do you need to include, and the resolution that you want to achieve. So because I'm interested, again, in galaxies with stellar populations, I really need to have as high resolution as I can. I want to study Milky Way mass galaxies because we know a lot about the star clusters in the Milky Way. So I generally use this technique, which is called a zoom-in technique, where I study individual galaxies. So these are where I study the cosmological evolution of like individual galaxies. But if you're interested in like having like a large number of statistics or having like a wide range of galaxies, then you might consider something like a periodic volume. And then you need to decide what type of numerical methods you're actually using for your gravity. So we all know that gravity is described by the Newtonian law, but how you actually implement that Newtonian law into the computer might have huge speed ups in terms of optimization, but it's also in terms of precision. So if your problem requires really precise gravitational interactions between the particles, you need to have a really good direct integrator for your gravity. But if you don't really mind about the precision of your gravity, there are other numerical methods that are much more efficient for a large number of particles. And similarly for hydrodynamics, there are different methods, there are different ways that we can solve the equations of hydro, depending on whether you're using a Lagrangian method, so you're looking at the evolution of a single element as it moves around in time, in space and time, or Eulerian methods. So you divide your volume in a grid, and then you're looking at what is happening at a given location within that grid. And then there are some hybrid methods as well. So depending on which one you choose, it has its perks, it has its caveats. There are some that are more efficient, there's some that are less efficient, depending on the exact problem that you're trying to study. But these are kind of like all the overall things that one needs to keep in mind when you say, okay, I want to do a numerical simulation. What do I need to consider? This figure is also by the review by Mark Vogelsberger, and it has just like a number of examples of things that have been done in the field. This is not complete, but it's a really nice compilation. And this figure is showing in the vertical axis simulations that are looking at either zoom-in galaxies, so just focusing on the evolution of a single galaxy in the top, or a large periodic volume at the bottom. And then the vertical axis is showing whether you only include gravity, so these would be like dark matter only type of galaxies, or whether you also include the effect of baryons. And I just want to show you two quick movies, because that's one of the things that we have in simulations, is like we get movies, which observers don't normally get. But like, so if we focus kind of like on large scale volumes, they've been growing in size, and they're capable of doing like really cool things. So when you model one of these large periodic volumes, the good thing that you get is that you get a large number of galaxies. So just to give you an idea of like some of the typical sizes, Illustrious TNG has three standard volumes, which is Illustrious 50, 100, and 300 megaparsecs on the side. Eagle, the standard Eagle is 100 megaparsecs on the side, but it has a high resolution of 25. Romulus 25 is 25 megaparsecs on the size. And those volumes are sort of large enough that it gives you a fairly large galaxy cluster. And so you have galactic environments that go all the way from like large galaxy clusters to dwarfs, if you trust your resolution. So this is a movie of coming from the Flamingo collaboration. This is a huge periodic volume. It has 2.8 gigaparsecs on the side. But because it's such a huge periodic volume, they're really they're running these volumes so they can have a huge number of galaxy clusters developing within this space. But they are very limited at the resolution that they can run. So a single resolution element in this simulation is 10 to the 9 solar masses. So think of a single dwarf encapsulated in a single resolution element. So if we let the evolution, this is just zooming in into one massive galaxy cluster at the center of the volume. You can see the scale bar, it's kind of increasing, we're zooming in, and then the resolution is sort of okay. But you see this massive galaxy cluster with like 2 large BCGs and lots of galaxies surrounding. Sorry, I should have said the color bar is showing the dark matter surface density in this volume. So, and this is just like this massive galaxy cluster we've seen, it's just like a tiny region within the volume. So if you're interested in statistics, this is the type of initial conditions that we need to consider. But it has a trade-off that like the type of physics, the type of baryonic physics that we're going to include are very crude just because the resolution elements are so huge. On the other hand, when we're looking at the evolution of single galaxies, we can do this zoom-in technique. And this is just, sorry, I should have said, we can do these zoom-in techniques if you're interested in doing like the cosmological evolution. Otherwise, you can also say, I just have one galaxy. I put my galaxy with a given profile in a box, and I just study this galaxy over a certain amount of time. That's also called isolated galaxies. And these are really good because then you can increase the resolution even further and like look at the details, for example, of, in this case, of the interstellar medium within this Milky Way mass galaxy. But if we look at what Fire 2 looks like for one of their galaxies, this is looking at the evolution of one of their Milky Way mass galaxies. There's going to be an LMC type merger on the side coming in. And you're looking at the evolution over the final giga year of this galaxy. The movie is rendered so that the 3 colors are showing the optical image of this galaxy. So blue is young star clusters, and the reddish is all the dust that is attenuating stellar light. But it had this movie, and then this movie is doing kind of like a flyby around the galaxy. And you can more or less see that with these type of initial conditions, we can include a much better description of the baryonic physics in galaxies. And so we have a better representation of what's going on within these particular type of systems. How long do I have? Okay, I can do the next video next one. So I just want to highlight one type of observable that it's not typically discussed of, but it's what I normally consider, which is that it's what I said. So I'm interested in looking at galaxies and their stellar populations, and in particular at star clusters, which are these gravitationally bound stellar systems. There are 3 reasons why I think they're fun. They're fun for their baryonic physics, but they're also fun for different dark matter models. The first one is that there's one type of galaxy that it's called ultra diffuse galaxies. So these are galaxies of the size of, or with the masses of dwarf, but with the size of a Milky Way. So there should be a galaxy in this image. If you cannot see one, it's fine. It's because it's ultra diffuse. But all of the bright spots that you can see scattered around in this galaxy are very massive star clusters. So a subset of these galaxies have a large population of very massive clusters. And so one of the suggested pathways for the formation of this type of system is that this was a normal dwarf, that it underwent a starburst, it produced a lot of star clusters, and the feedback from these star clusters just blew out the galaxy. But if you happen to change the underlying dark matter model for this type of galaxy, and for example, you have a shallower potential for your dark matter profile, maybe you don't need as much of an input of the feedback from star clusters. So it's an interesting type of scenario where changing the dark matter model can have interesting consequences. The other one is that we're seeing very bright star clusters at higher and higher redshift. This is a lens galaxy at redshift 6. Viewed in a UV band, and you can see all of these very bright and compact clumps. These are stellar clusters that are kind of leaking their UV luminosity from the galaxy. And so because we're seeing this leakage of UV luminosity, there's the idea that maybe the ionizing radiation can also leak from the galaxy, so star clusters could be sources for organization. But if you change the nature of their matter, then you can change the halo mass function. You could change the type of halos where these first star clusters are forming and whether they contribute to radionization or not. And the last example I have is that we're seeing that the spatial distribution of bright star clusters in galaxy clusters correlates really, really well with the underlying mass distribution. This is some work that I've been doing together with Bill Harris at McMaster University. And the background image is showing the predicted mass distribution from strong lensing. And these blue contours are the spatial distribution of the glowler. So we have a primary clump, 2 BCGs, and an upper BCG up there. Let me see if there's a laser. Oh, yes, perfect. So we have like the other one up here. So if you change the nature of dark matter, you would see shifts in this correlation that I think are possibly quite interesting. So there are different ways that you can include star clusters in this formulation of galaxies so that you take into account their formation and their evolution. So if you focus on kind of this group of stars here, which is meant to represent a star cluster, one of the first things we can say is say, okay, well, I want to do, I want to look at the entire evolution of a single galaxy over cosmic time, but then I'm very limited at resolution. So now what I call a star, it's 1,000 to 10 to the 5 solar mass resolution element that is actually a single stellar population, and I'm resolving their gravitational interactions on the scales of like 100 parsecs. In this case, star clusters have to be subgrid, so they have to be below the scale of what we can resolve. And this is just an example of something I did during my thesis, where you're seeing the collapse of a single Milky Way mass galaxy with its stellar population, and it has satellites that are coming in. So this type of simulations is great because then we can compare the properties of these star clusters with what we see in the local universe and see how closely related they are. On the other extreme, if you again focus on these just 3 particles that describe your star clusters, we can say, okay, what if I just increase the resolution of my simulation? I have like a single star representing a single star within the star cluster. Then you can do this type of simulations where you have a number of particles describing a single star clusters. And you can see how, for example, this one is driving a super bubble around it. There's another one over here. These type of simulations are really cool. The problem is that then you're limited on the type of galactic systems that you can model. These are typically low mass dwarfs, modeled over like a few hundred mega years. Yeah, I don't know what that beep is. Is there anything I can do? Maybe I stay away. Yeah, because there's some interference with the microphones, I guess. Okay. It's my what? Is your microphone attached to this? Yes. Oh, I'll just hold it. Sorry about that. Okay, yeah, so the last thing is that you can say, well, I do not care about what's happening within the star cluster. I really want to have the feedback from the star cluster onto the galaxy because that's driving the evolution of the galaxy. So then you can do this type of numerical simulations where you're now looking just as a single cloud. This is not a galaxy, but then it has a population of star clusters that are forming. There's going to be a very massive blob coming up in a second that's going to destroy the entire galaxy with its feedback. So there are different numerical methods that you can do, but the idea is that by including star clusters within numerical simulations, we can study a new type of observable. So that's going to be my summary, which is that If you're delving into the field, into the realm of galaxy formation, you should be aware that it's a bumpy road ahead because it's a multi-scale, multi-physics problem. And what physics and what scales exactly you should be looking at depends on the exact science question that you want to answer. You should view numerical simulations as just numerical experiments and trying to include as much as is relevant for your problem, but not try to solve the entire universe. And as I said, if you include, by including new or more baryonic physics, we have new observables for that matter. And I think I'm good, perfect.
Thank you so much.